Hey guys, this is our last lecture before we actually get to probability. The last two lectures were lectures on counting, and this is going to be a review of sets. So everything in probability basically is built upon set theory. So I want to make sure you guys are comfortable with sets before we move on to starting probability. From discrete math, if you haven't had discrete math, we'll cover things, hopefully you'll pick it up. There's two different ways to represent sets. So if I have a set A, say that A is a set, I could use this, we use curly braces to talk about the elements that belong to A. And we could say that A maybe is the set containing X, Y, Z. So this is everything in A. Or maybe B equals the set 1, 2, 3. So we can write a set like this if we can list all the elements within the set. Sometimes we have to use a little bit different notation though. So suppose we wanted the set of numbers between 1 and 2 on the real number line. So this is the real number line. And we want to have a set of all these numbers between 1 and 2. So that includes 1.1, 1.3, 1.768, and so on, any decimal expansion that you can make. I mean, it would include 1.33333 repeating, being 1 1/3. So we, of course, can't just write out all the elements within this set. So sometimes we also use the notation, I'll call it a set C. We still use the curly braces, but what we're going to do is write something along the lines of X such that, so for such that you can use a vertical bar or colons. I'll use colons. So X such that 1 is less than X is less than 2. So here you say this is the symbol that is going to be the set elements, and here's the rule the symbol must follow to belong to the set. So, for example, the point 3/2 is an element of C. And this symbol is the membership symbol, so this is membership. And we use it to denote belongs to. So 3/2 is an element of C. 2 belongs to B. It's an element of B. X is an element of A. If we want to say something is not a member of a set, you just write a slash through the membership symbol. So for example, X is an A, Y is an A, but W is not an A. So you write the membership symbol with a slash through it to say that W isn't an element of A. Likewise, we could say that 3/2 is not in B. And in C, my rule was strictly less than. X has to be less than 2. So 2 is not an element of C. So that's the two basic ways we represent sets. I'll just remind you that sets don't actually have a definition, so we're not going to try to define sets. We just think of them as collections of things. So A is the collection of the symbols X, Y, Z. B is the collection of numbers 1, 2, 3. C is this piece of the real line, which we represent as all X between 1 and 2. So let's keep A as it was. So A is the set X, Y, Z, and say B is the set W, X, Y, Z. Then for every A belonging to A, so here A is a symbol that represents either X, Y, or Z. If for everything in A is also an element of B. So in other words, X is an A, so X is in B. Y is an A, so Y is in B. Z is an A, so Z is in B. And there's also some elements in B that aren't in A. Whenever this happens, so everything in A is also in B, we use this symbol that looks kind of like an elongated C. So we say that A is a subset of B, or A is contained in B. And we denote it like this. So A is a subset of B. Or equivalently, you could say A is contained in B. So let's do one more example. Say that C is the set that it was before. So it's all elements between 1 and 2. So all numbers between 1 and 2. Again, it's this part of the real number line from 1 to 2, and it's just like this. And say that D is going to be the set X such that 1 is less than X is less than 3. So this was our picture of C. Now we draw a picture of D. It goes from 1 all the way over to 3, and it includes all of this. So notice that any point in C, if I pick a point in here, that point's also a point in D. So 3/2 is in C, but 3/2 is also in D. And anything in C is also in D. So we'll have C as a subset of D, since D includes more points. And we often use subsets to check for equality of sets. So we write A is a subset of D if for every X in A, X is in D. And we say A equals B if whenever X is in A, X is also in B, and whenever X is in B, X is also in A. In other words, they contain the same things. So a simple example, say that A is the set 1, 2, and B is the set 1, 2, then we say that A equals B. So it seems kind of obvious, hopefully it is. I did want to define it because it's not the same thing as equality of numbers. It's not quantities. It's do these sets both contain the same objects within them? And if they do, then we say the two sets are equal. So it's a relation. Okay, and what does this have to do with the contains? So let's relate these two. So we'll say proposition, which I'm not going to prove anything in these videos. Maybe we'll talk about this more in class, although you should already know it from your previous classes. But A equals B if and only if A is contained in B and B is contained in A. So notice this happens in our example. Everything in A, if I pick an element in here, it's going to also be in B. So we have that A is contained in B. But also if I pick an element in B, it's going to be in A. So B is contained in A. And so the two sets must be equal. And the only way they can contain each other is if they have exactly the same elements, which means they have to be equal. And this is often how a proof goes. So if we want to show two sets are the same, a common technique is to show that they're contained within each other. So you show A is contained in B and B is contained in A, and then conclude that they must be equal. So that's our basic notation of how we write sets whenever we want to say elements are in sets or not in sets. And you can do the same thing with contained in and not contained in. So if you want to say a set is not contained within a set, just draw a slash through it, just like you did with the membership symbol. But let's move on. So we can take two sets and create new sets. If A and B are sets, define what we write. We write A and then we write this little U symbol in a B. It's not actually a U, so please don't put a tail on it. It's not this. It's just like this. It's a cup or something. It's up. It just goes up on both ends. And this is read A union B to be the set just say by. So it's going to be by the rule. X is an element of A union B if X is an element of A or X is an element of B. And remember that this or here, this is the mathematical or. In math, we always use the inclusive or by default, so this is inclusive. So if A is equal to the set 1, 2, and B is equal to the set 1, 4, then A union B is equal to the set. So 1 counts because 1's in A or B. In fact, it's in both. And that's what we mean by inclusive or. So if it's in both, we still count it. We only count it once, because what this list tells us is only if the element's in the set or if it's not in the set. It doesn't make sense to say it's in the set twice. It's kind of like saying, am I in the room or am I not in the room? I can't be in the room 2 times just because I've entered the room more than once, say. We just write 1 time, even though it's in both these sets. Likewise, 2 is in A or B because it's an A. So if I were to ask you, is 2 an element of A or B? You'd say yes because it's an A. So we count 2, and likewise we count 4 because 4 is an element of A or B. So the union A union B includes all the elements that are in A or B, 1, 2, and 4. Notice that it gets bigger. So one direct result, I'm just saying it gets bigger. What do I mean? A is contained in A union B. If something's in A, then it's going to be in the union. Likewise, B is contained in A union B. So what I was referring to with the slash symbol, we also can see here that in this particular example, A union B is not contained in A in this example. And why is that? Well, 4 is an element of A union B, but 4 is not an element of A. So it fails the definition of subset or contained. So that was one of our operations. We take 2 sets and we create a new set by doing this union. A very similar operation. Let's see, what do I need to erase here? Not very much. So if A and B are sets, we define A intersect B. So this is just, you flip the symbol over. It now looks kind of like an N. This is A intersect B. So it's the intersection, or what's contained in both of them, by X is in A intersect B if X is in A and X is in B. So this is the key difference. It's not an or, it's an and now. So let's take our same sets, A and B, and let's find the set that's A intersect B. So now we only include those things which are in both A and B. So 1 is in A and 1 is in B. So 1 goes in the set. 2 is in A, but we can't say 2 is in A and B because 2 is not in B. Likewise, we can't say that 4 is in A and B because 4 is not in A. So the only thing we're actually going to count is 1. The intersection of A and B is 1. That's where the 2 sets overlap. Hopefully this is pretty basic for you guys. You should have gotten comfortable with this last semester. Oh my goodness. We're not going to have time in this video to get through all of the review. So I might have to make a second video on set theory.